We're going to move on today then from the electric field to the energy that's associated with the electric field. And this is mirroring what we did when we studied the gravitational field. And then we moved on to the energy associated with the gravitational field. So if you remember, we studied gravitational potential energy. And today we're going to study electrical potential energy. So that's your title for today. What I'm going to do is mirror what I did with the gravitational potential energy. Oops, can't spell energy. And that will be good revision of what we did do at that time as well in terms of the analysis. I'll just skip out some of the integrations that we did for the gravitational field because you don't need to see the mathematics twice when it's technically not even something that is included in this course. Okay, so let us consider that we have got a charged particle Q, which for the sake of what we're about to do today, we'll assume is a positive charge, but you'll see later on that the argument works equally well for negative charges as well. And then we'll have a second charge, which we'll call little q, and we'll assume that that one is also positively charged. And you know from what we have been studying that little q is experiencing a repulsive force due to big Q, which is 1 over 4 pi epsilon 0 QQ over R squared. What we now want to consider is how difficult it will be to move that charge towards big Q. So if we're going to, if little q had started further away and we've just dragged it inwards to this point, how did we do that and how much energy did it cost to get to this point R, where R is the separation of the charges? Well, if we wanted to get q to this point, we would have had to have pushed on it. And we're going to have to push on it in this direction because its natural tendency is to be repelled away. And this is a radial force from Q, so we're going to have to push directly towards Q. And we could push with any size force, but it needs to be at least the size of F, because otherwise the resultant force will be away from big Q. And if we use a force that's bigger than the Coulomb repulsion, then we will succeed in moving little q towards big Q. But as we do so, little q will accelerate and gain kinetic energy. And that's not the question I just asked. All I'm asking is about moving it to this point, not to invest a whole load of kinetic energy in it by the time it gets there. So what we're going to assume is that we're actually pushing it with exactly the same force. Now, there might need to be a moment of acceleration at the beginning just to get it moving, but for the vast majority of its journey inwards from wherever it was to this distance R, we're going to push it with exactly the same repulsive force as it's experiencing so that the forces on the charge are balanced and it moves inwards at a constant velocity. And we're interested in the amount of energy that we transfer to the charge. So we're going to do work on the charge using this force. And you remember that work done is a transfer of energy. And so by the time we have finished transferring some energy to this charge by doing work on it, the charge will have associated with it a pot of energy that it didn't when it was over here somewhere. And we're going to give that little pot of energy a name, because after we have stopped applying the force, we've gone away and left the charge all where it is. It has, the consequent has associated with it what we are going to refer to as the electrical potential energy. Now, you might remember from when we did gravitational fields that what we really need to do is do force times distance, where distance is however far it's come from wherever it was. The problem with that is that the force itself is distance dependent. And so as the charge moves through a distance d to arrive at this point here, we are left with the problem that if we just do F times D, which F do we use? The force here or here or here or here, because it's a different force every single value of R. So what we do need to do instead is multiply F at R by a tiny, tiny little distance over which R changes by a tiny little amount. And then we need to add all of those contributions up all the way from all the R's that are all the way over here, all the way inwards, bit by bit by bit by bit by bit, until we get to this R. So that altogether, the sum of all the delta R's adds up to the distance moved. But the work done each time will be using a different value of R every time we change the separation from big Q. And you might remember that we have a mathematical formalism for doing this. So instead of a finite number of sums, we do an infinite number of sums. And we do that by making dr infinitesimally small. In fact, we allow its size to tend to 0. And when that happens, this ceases to be a summation and starts to be what we refer to as an integral. And I know lots of you are familiar with this from your maths. If we were to carry out that integral, we then need to decide where we are integrating it from and to. So for the purposes of our discussion today, and you might remember why we do this from our discussion of gravitation, we're going to integrate it from a distance that began at infinity, and we're going to bring the charge all the way in from infinity until it reaches a distance r from Q. So that's the integration that we're going to do today, or actually I'm going to skip it out. And then that's the function of R that's going to go in there. Now, when we do that integration, I'm not going to write it out, but for the mathematicians, you can see all of this part of the function of the force is a constant, which means that really what we're just integrating here is 1 over r squared. And when we do integrate 1 over r squared, you remember that that will become a 1 over r, but it'll have a minus sign in front of it. But then when we put the limits in, we're going to have 1 over infinity 0 minus 1 over r here, which will turn back into a positive. So when we do that calculation and we end up with our answer, we end up with the electrical potential energy, which is the work done moving the charge from infinity to r from Q. That's going to be equal to 1 over 4 pi epsilon naught QQ over R. And I told you when we studied gravitational fields that students quite often find these two equations a little bit too close to each other for comfort, that they only differ in this r squared versus this r here. And it's a common thing for students to muddle the two equations up. So try to remember that it's an inverse square law for the force, but it's just 1 over r for the energy. Now, what really upsets me about your textbook, which I do like most of the time, I really do like your textbook, but there are a couple of little things in it that drive me nuts. And one of them is that rather than using an E subscript P for this formula, or just the letters EPE, in the textbook, your author has decided to refer to this formula by just E. Whereas just 3 pages earlier, they have just referred to the electric field strength as E, which is back to having the R squared in it. And given that it is such a common mistake to muddle all these formulas up, I'm furious at your textbook author for referring to this as E 3 pages after they referred to this as E. So you have my permission to change your textbook in a permanent pen to just insert a subscript P everywhere you see E equals that without a squared here. Bad textbook author person. Okay, moan over. So this is the amount of work that has been done moving a particle from infinity to here. And you can see that if we put infinity into this equation as r, then the whole thing becomes 0. And that's what we discussed as being an appropriate value when we did gravitational fields. That if these two objects are an infinite distance apart, then presumably they can't exert any meaningful influence on each other, and therefore there should not be any energy associated with each other. So when the charge is an infinite distance away, it has 0 electrical potential energy. And then as we move the charge closer and closer and closer and closer and closer, fighting against the repulsion, we do work on the charge, and it increases in energy until when it gets to this point here, it has got a finite amount of energy given by this formula here. And there are some examples that I'm going to leave you with at the end of today's lesson in which you have to put numbers into this equation just to make sure that you can. And the purpose of that exercise is simply for you to become familiar with the idea that you don't always press the squared button when you've got this formula. Square it for the force, don't square it for the energy. I would like to highlight a difference, though, between the gravitational and the electric potential energies. When we did GPE, our constant of proportionality was G, not that. And we had a pair of M's rather than a pair of charges. And we had the 1/r relationship. But if you remember, there was a minus sign at the front of the equation. And the reason that there was a minus sign at the front of the equation is because the gravitational force is an attractive force, not a repulsive force. And so the gravitational force is this arrow, and the work done force is this arrow, other way around to what we've just discussed. Which means that when we're doing work on the charge, we're actually moving the charge not from infinity, but to infinity. And if we want it to have 0 energy when it gets to infinity, then it needs to have a negative amount of energy here. And that's why there's a minus sign on the gravitational potential energy, because it's an attractive force, not a repulsive force. In the case of our positive repelling positive charge, because it's a repulsive force, it begins at 0 energy, and then we top it up as we bring it in so that it really does end up with a positive energy when it gets here. So you need to remember that this is a positive formula here. We don't bother printing the positive sign, but it is a positive formula. Whereas the same formula for the gravitational potential energy has a negative in it. That's because this is a repulsive force, and this is an attractive force. However, you know that the electric force can be attractive, and if Q was to become negative, then this entire number will become negative, and we will again have a negative energy for our electric potential energy, just like we have a negative energy for our gravitational potential energy. So they are symmetrical. They do behave in the same way. It's just the gravitational potential energy formula can only represent an attractive force, but the electric potential energy can represent an attractive or a repulsive force. So it's attractive, it's negative when it's attractive, and it's positive when it's repulsive. Okay. That's your formula for the amount of work done required to move a charge from an infinite distance away to just a set distance r away from another charge. We're now going to carry on with the same arguments that we did when we did gravitational potential energy, and to state that again, we're going to break the symmetry between the two charges. And we're going to talk about not a specific charge Q, but an any value you like charge Q that comes in. So we're going to separate out the things. So again, we can put the Q down here, and we can have that Q down there. And when we go through all of the analysis, we can have this Q down here. It's just a little subtle trick to just move the Q. It's mathematically identical, and we did exactly the same thing in the gravitational potential energy formula as well. And then what we said was, okay, well, if all we're doing is scaling by Q, then let's talk about the electrical potential energy per unit charge, just like we spoke about the gravitational potential energy per unit mass. So this per unit mass was just obtained by setting m to be 1. And likewise, this per unit charge is obtained by just setting q equal to 1. So rather than having any old charge coming in, we'll have 1 coulomb of charge instead. And that way, we're going to be dealing with effectively the electric field, because that's the force per unit charge. And now you can see why we really do need the subscript P. And so this is the gravitational potential energy per unit mass, Gm over R, and the electrical potential energy per unit charge, 1 over 4 pi epsilon naught Q over R. Okay, this is great, but we historically, if you remember, have done something very annoying. And instead of referring to this as the electrical potential energy per unit charge, which everyone will be comfortable with, and it says exactly what it is, and we all know where we stand. Somebody decided once upon a time that it was a very sensible decision to lose the word energy, because you know what, we can all remember that it's an energy. And you know what, why not? Let's just lose the per unit charge as well, because we all know what we're talking about. It's not like we've got any students that we need to teach all this new physics to, and they're not going to get confused one day if we do this. So let's just call it, you know what, the electrical potential. And that's what we're going to call this now. Not the EPE, we'll just call it the electrical potential. Because who needs to put the word energy in the name of an energy? And who needs to write per unit charge when it's per unit charge? We'll all just agree to remember, because it's such a great name. Sorry for the sarcasm. Okay, in moving 1 coulomb of charge. And we did this for the gravitational potential as well. The grav pot. So the electrical potential, you probably should write what I have written down with these crossings out and maybe make a note to yourself that this was a moment of stupidity that physics should hang its head in shame about. But we didn't stop there, of course, because we went on to give this thing a letter. And when we studied gravity, we called it V. Obviously, why wouldn't we? V for the gravitational potential. Made so much sense at the time. But now we are in a position to at least understand the origin of V. So let's just stick to electricity for a second. So let me get rid of those force arrows as well. So if we move this 1 coulomb charge from here to here, then its electrical potential at this point, let's call that R1, and then we'll move it into a position R2. And if we want to know what the difference is, how much extra work we did moving from there to there, well, that was the work we'd already put in. So that's the amount of energy it has by the time it gets to this point. And then we put in some extra work to move it to this point, at which point it will have that amount of electrical potential. And so if we just subtract one from each other, then this is now the difference in electrical potential, which over time, in a similar way that we shortened this name from electrical potential energy per unit charge to just electrical potential, as time went on, we ended up just referring this to the PD, the potential difference. Now, for a pair of point charges, this is the algebraic expression for it, but we are much more familiar with referring to potential difference, not between a pair of point charges, but between 2 points in an electrical conductor, like a copper wire that's carrying a current of free electrons. Now, it's important that you understand that a copper wire with uncountable numbers of positive charges forming that ionic lattice surrounded by the free electrons that are drifting past it, that is absolutely not a situation of a pair of point charges. And so this formula will not give us the difference in charge between 2 points, the difference in electrical potential between 2 points in a wire, or 2 points either side of a component in a circuit. So this isn't the correct algebra for that, but the principle remains the same, that there are 2 locations that happen to have a light bulb either side of it, between them, but that's irrelevant. There exist 2 places, and we have done a certain amount of work on the charges to get them to the entrance point to a bulb. And then when they come out of the other side of the bulb, they will have a different amount of electrical potential associated with them. And so we can talk about the electrical potential energy difference per unit charge either side of the bulb. And we might not be very able to calculate that because there are so many charges involved, but we can certainly measure it. And we've been measuring it for a long time. before it was called electrical potential energy per unit charge, before it was called electrical potential, before it was called difference in electrical potential, before it was called PD, we were calling it voltage, and we were measuring it with a voltmeter in a unit called volts, and we were referring to it by a letter V. And therefore, this is the letter that we use for the electrical potential, and also the difference in electrical potential. I suppose that should be more accurately delta V, but we never bother, do we? We always refer to it as just simply V, as if it's taken for granted that we're measuring it not to the point R1, but to infinity, where it's 0. So we often don't bother with the delta V. You've never written delta V when you've been doing your electrical equations. You've always just said the potential difference is V equals 6 volts or something like that, but technically. So that's the origin of the capital letter V for our choice of algebraic variable for electrical potential. Okay. It is so easy to model up the electrical potential, which has no little q, with the electrical potential energy, which does have a little q. It's really easy to model up V with E, the electric field, which doesn't have the little q, but it has an r squared there. And it's really easy to model up the electrical potential energy with the force, which has the q. They both have the q, but the force has the r squared on it. And we've met this problem before when we were doing gravity. There were 4 formulae there as well, and I stressed and stressed and stressed how easy it was to model up those 4 quantities there. It's the same 4 quantities here. Again, easily modeled up. But now it's even harder, because now you've got 8 formulae. You've got the 4 for gravity and the 4 for electricity. And while I don't think that you're going to model up the electrical ones with the gravitational ones, you've got to remember that the gravitational ones have a negative sign there, but the electric ones have a positive sign there. I mentioned when we studied gravitational fields that 20 or so years ago, we took gravitational potential and electrical potential off the A-level specification because students got so muddled up between all of the similar definitions and the similar formulae. But it was put back on again about 4 years ago. So it's your challenge now to make sure that you do not get confused and that you do manage to stay on top of all of these different definitions and formulae, and that you apply the right ones in the right situations. To that end, in a minute, I'm going to leave you with some questions in order for you to be able to do that. 2 little things to finish off though. I just want to make the point that this electrical potential energy, or the electric potential, whichever one you want to talk about, is actually given to us by the area under a force distance graph. So if it is force times distance, then that's an inverse square shape, 1/4 pi epsilon naught QQ over r squared. And what we're talking about is that the difference in electrical potential energy between 2 points will be the area underneath that graph, which is what the integral is. And the electrical potential energy full stop, which is the work done moving the charge from infinity, is the area of this graph all the way out to infinity. If, on the other hand, you want to know the electric potential, then we just need to switch from F to E, and now the area under this graph of an electric field graph rather than the force graph, the area under this graph will now give us that. So that's the first little thing that I just wanted to tidy up. Again, it's something we've discussed many times, that the work done is the area underneath a force distance graph. But the second thing that I want to just do before we stop today is to give you glance into how something like this is then taken forward at a university level, because we're reaching the end of the course now, and many of you will be going on to study the sciences or maths or applied maths or engineering, electrical engineering, physics, chemistry. If you are going, and I know lots of you are going on to study things like this, I'm going to take any opportunities I can to kind of show you how a general approach that we take at A-level can be applied to a very niche, narrow area of a particular phenomenon. And once you take the very general theory and you strip it down and focus it down onto a particular scenario, it's interesting to watch how the theory manifests in this specific scenario. And so I'm just going to give you an example of electrical potential in a specific scenario. So this isn't particularly examinable, although it is mentioned on your specification. I've never seen it examined, but it's an interesting exercise in going from the very, very general to the very, very specific. So many of you will have been electrocuted by one of your physics teachers lower down the school by us inviting you to hold on to the dome of a Van de Graaff generator. And you remember that this is a big metal sphere on an insulating support. And usually there's another sphere as well, which is on another insulated support, often in the teacher's hand. And you charge one of them up to a very, very positive value and the other one to a very, very negative value. And then you usually get some kind of discharge that happens between the two. So hopefully you remember what a Van de Graaff generator is. But let's turn the Van de Graaff generator off and not have the other sphere. Let's just have a positive sphere on an insulating support. And instead, I'll just bring out a 5,000 volt power supply. There's no real need for it to be 5,000 volts, but it's more fun if we use a larger voltage. And I'll just take the positive terminal and I'll just tap the positive lead against the metal dome. And what that means is that the other end of this, the negative side or the other terminal, say it's earthed, which means basically that we're keeping it at 0 volts. So there's no imbalance of charge over here, and no work done is required to put charges in this place. So this is effectively our infinity. It's a place of 0 energy. What's happening is that this 5,000 volt power supply is moving charges from here, where they have no energy, and it's doing work on them, and it's bringing them all the way over here and popping them onto this sphere. So when it adds a charge to this sphere, the charge will, you might imagine that the charge will land all over the sphere, but remember the charges are positive and they're repelling each other. So in actual fact, they're going to push each other all away, and they're going to do their best to get as far away from each other as they can. And so as I add the charges to this positive sphere, the positive charges are actually going to line themselves up. Now, we're speaking very abstractly in that I'm moving positive charge. You know full well that an electrical supply is doing no such thing. We're just thinking hypothetically that I have grabbed some positive charges from infinity and I am moving them with a force all the way from infinity to here. That's the hypothetical that's going on. What's actually happening, of course, is that the positive charges are already there in the metal structure. And what I am doing is extracting electrons. So rather than actually moving positive charges inwards, I'm actually moving negative charges outwards. the effect is the same. The remaining electrons become attracted throughout the positive dome, and we end up with a net positive charge on the top of the sphere. It doesn't matter in physics how you achieved something, usually. So had I jumped in my spaceship and visited infinity and picked up a whole load of positive charge and brought it all the way in and dumped it on that sphere, or if I had just used this power supply and dumped it on the sphere, it doesn't matter. The effect is the same. I have ended up with a whole load of charge that used to be in a neutral place and is now in a charged place. And the amount of work that I have done, either in my imaginary spaceship to achieve this charged dome or using my power pack, is 5,000 joules for every coulomb that I moved. So what's this got to do with what we've just been talking about? Well, we've just written down a formula that says that V equals 1 over 4 pi epsilon 0 Q over R. And because these charges are on the surface of the dome, R is the radius of the dome. So what has this formula got to do with this? Well, we've just studied a concept called capacitance, which is the amount of charge stored per unit potential difference. And when we were talking about capacitance, we were definitely talking about a pair of plates of which the electrons from one plate had been moved around an external circuit onto the other plate. And so these were flat objects, a little distance apart from each other. There were two of them. One of them was positive, one of them was negative. When we spoke about capacitance or capacitors, this was our arrangement. Certainly, we never mentioned anything about capacitors looking like this. But if I take you back to the very beginning of the capacitance topic, I defined capacitance as the ability of an object to store charge. We happen to like a pair of parallel plates because the arrangement is easy to manufacture, easy to shrink, easy to predict what will happen next. They're very robust. They store a lot of charge. We like the parallel plate capacitor, but the parallel plate capacitor isn't the only way to store charge. And this object, believe it or not, it counts as a capacitor. It's an object that is storing charge. It doesn't even have a second plate unless you want to consider that infinity is its plate or an earth wire is its other plate. So, well, we need a Q over a V. Well, if I just divide through by V and multiply up by the rest of it, then you can see that Q over V from this formula is just equal to that. And so a really specialized niche, tiny little application of our formula, which was all about energy, remember, we don't need the 5,000 volts, is actually the realization that an isolated charged sphere, or an isolated sphere, actually counts as a capacitor, and its ability to store charge is given by this formula, which came from this potential formula. And there are lots and lots and lots of examples of this that will be in your future if you have decided to study a science or maths-based course at university, where you study a general theory that applies in any situation, and then you close it down to a very, very specific situation, and you end up with a conclusion, which is that, in this case, an isolated charged sphere is a capacitor. How much charge does it store? How would you have even gone about answering that question if you didn't know about electrical potential and you didn't have a relationship between Q over V from here? So if I'd have just started today's lesson with, hey guys, let's ask ourselves what the capacitance of this crazy sphere is, how would you have even begun that? And it underlines how knowing a lot of physics, or a lot of anything, allows you to make connections and come to conclusions that a person with less knowledge wouldn't have been able to do.